The goal of this video is to talk about right triangles, to try to find the side lengths of a right triangle. And there are certain angles, if you have them in a right triangle, it'll make them easier to find all the side lengths. So we'll talk about right triangle. So there's a 90-degree angle, but having a second angle in that triangle being 30 degrees. And so a picture of that will look, roughly something like this. And there'll be the 30-degree angle. That's the small angle right there. We'll also talk about the case of a right triangle where one other angle is 45 degrees, so maybe that's the right angle right there. And the picture of something like that will look roughly like this with the 45-degree angle right there. And we'll also talk about the right triangle which has a 60-degree angle in it. So if you draw 60 degrees as an angle, roughly something like this. There's that right angle and 60 degrees right there. And incidentally, this angle right here happens to be 60 degrees. So the case of 30 degrees and the case of 60 degrees will be really related to each other. For reasons you'll see later, we'll start talking about the 60-degree angle. We'll talk about the 30-degree angle next, and then we'll take a moment to pause and talk about the relationship between the two. And then we'll end the video on talking about the 45-degree angle. There is one thing I just want to keep making note of, and the whole idea is in these pictures, because the three angles always add up to 180 degrees, you'll always know all the angles, right? One is 90 degrees, one is one of these numbers, and then the other you get by subtracting from 180 degrees. So you know all the angles, and the point is when you know all the angles and you don't have any of the sides, well, we need to find the three side lengths. So there's a first side, and knowing the first side length will hopefully get to the second side length, and knowing two of the sides hopefully gets you to knowing all three of the sides. And this is what you need in order to talk about the trigonometry involved. Now, starting from, I guess you start by knowing none of the sides. And how do you get to one of the sides? Here you just pick the length of one of the sides, and it'll, there's a good choice to make in each case, and we'll talk about that. Okay, the thing is we're dealing with a right triangle, so if you know two of the sides, then it's not too bad to find the third side. So to find the third side, you can always get the third side with the Pythagorean theorem. Okay, so that's not going to be so bad. The tricky part is going to be this step right here, right? So you pick one side. It'd be nice if we knew a second side, and once you know two sides, you get the last side using Pythagorean. So how do you get the second side? Well, here you're going to have to use some special properties of these triangles. You don't get to pick this side. So picking this side, that is not what we're going to do at all. But due to the special shape of these particular triangles, the process will not be so bad. So let's start with a 60-degree angle. So we're going to talk about theta is 60 degrees, but here's how we're going to talk about this. We will not start with that right triangle. We'll instead start with an equilateral triangle. Now I'll do my best job here to try to draw that. So that means you have a 60-degree angle there, you have a 60-degree angle up there, and you have a 60-degree angle there. The thing about an equilateral triangle is that all three side lengths are the same. So you can pick this side over here to be any length you want. Any number will work at all. This math will work out a little better by picking an even number. So I think we did 2 in class. Let's just use a 4 here just to try something different. Now by picking this side to be 4, you copy this 4 over here, and you copy that 4 down here, right? We didn't actually pick all 3 sides to be 4. Really the idea is you pick one side and the other 2 become 4. Now what we're going to do is take this 60-degree angle that's right here and cut this angle in half. Now, by cutting in half, actually you're going to get two 30-degree angles. Okay, that's one thing that happens. This cut, just due to my picture might not show it here, but just to the mere shape of this 60-degree, 60-degree, 60 triangle that you started with, this also, as a second feature, creates a right angle right there. Okay, so you actually have 60 degrees, 30 degrees, 90 degrees, all those add up to 180 degrees. And finally, this line, which made this 90-degree angle and cut this 60-degree angle into 2 equal-sized pieces, does one other nice thing. It actually cuts this side into 2 equal-sized pieces of length 2. Now, here's the point. We're going to take this triangle. Let me see if I can highlight this triangle. This one, maybe I'll just highlight the outline of it. This is getting messy, sorry about that. But let's take that triangle and try to draw that over on the side, like this. Okay, so I've tried to replicate what I already have there, just try to make it as much to scale as possible. 90-degree angle, 60-degree angle, there's a 30-degree angle. You don't even have to label that 30-degree angle, it's just nice to see that that's there. And just copy the information we already have, like this length of 4 and this length of 2. Now notice, we did not choose 2. Right? The idea is this 2's copied from here, and where did the 2 come from? This was not chosen here either. It was computed by taking this side, which was 4, and cutting it in half. Right? 4 divided by 2 is 2. So that's how we get that second side, and then we have this remaining mystery third side we'll call z. Use the Pythagorean theorem to find it. You have 2 squared plus z squared is equal to 4 squared. So 4 plus z squared is equal to 16. You have z squared is equal to 12 by subtracting 4 on both sides. And so you get z is equal to plus or minus. There's always a plus or minus when you square root both sides of an equation. You get a root 12 there. All that really makes sense is to say that z is positive, so you really have a positive root 12. And there's a nicer way to write this root 12. This is written as root 4 times 3, and then there's a property that says square root of a product is the product of square roots. So you get root 4 times root 3, and that is, well, root 4 is 2, and then you have a root 3. So this side z, now we don't have to label this with a z anymore. You could erase this or something. I'll just rewrite though down here that z is equal to 2 root 3. And now you have the 3 sides, so you can go ahead and write out, sorry, this is a little unorganized, but let me write this over here. You can write out that sine of 60 degrees, which is opposite over hypotenuse. You have 2 root 3 over 4. That simplifies a little by canceling 2's, and you have root 3 over 2. That's the familiar number, that's sine of 60 degrees. And it doesn't matter what number you start with here. Cosine of 60 degrees is adjacent, that's the 2 over the 4, so you get 1/2. And finally, tangent of 60 degrees is this opposite over adjacent, so 2 root 3 over 2, and you get a root 3 from that. Now the information you need for theta is equal to 30 degrees is already in place in that last equilateral triangle. So you can read off what you need there. Just make sure you read from the correct vantage point, let's say, and just, you know, what the hypotenuse stays the same, but what's opposite and what's adjacent change. A different way to do this is to actually start with an equilateral triangle, and just due to our conventions, it's maybe a little easier to draw a slightly rotated equilateral triangle. Same thing as before, you pick some numbers. Maybe we'll just pick 2 as the number for the length of each side this time. But same idea as before. What you do is you take one of the angles, and here it'll be, I guess, most convenient to do this one. Here, by cutting in half, you get a 30-degree angle right there. You get this right angle right there, and on the other side. And then finally this 2, you have 2 pieces over here, which are length 1, and this is the interesting one. Now if you take this right triangle that you see right here, we'll draw this off to the side because our picture's already messy. So trying to get this accurate, you have here, this is a 30-degree angle, you have a 60-degree angle, and the 90's already been written. You have that hypotenuse of 2, there's this side 1, and this mystery side, let's call that z for now, and then we can write out the Pythagorean theorem. So z squared plus 1 squared, notice we didn't pick the 1, it was computed, is equal to 2 squared. So you have z squared plus 1 is equal to 4, z squared is equal to 3 by subtracting 1 on both sides. Square root both sides, so z is equal to plus or minus root 3, and due to the fact that z has to be positive, the only number that's going to make sense is z is equal to the positive square root of 3. So instead of labeling a z here, let's go ahead and erase this time. I mean, we've done what we needed with z here, but now we can replace that with a root 3 right there. So now we have all of the things that we need in order to talk about sine, cosine, and tangent of this angle. So sine of 30 degrees is opposite, so 1 over hypotenuse 2, and then cosine of 30 degrees is this adjacent side, this root 3 over 2, and then tangent of 30 degrees is 1 over root 3, opposite over adjacent, and there's a different way to write this, 1 over, so I just copied it first, okay, so copy this 1 over root 3, but I'm going to multiply by 1, and here's what the 1 looks like. That 1 I'm going to write is in the form root 3 over root 3. Multiply these fractions, so 1 times root 3 is root 3, and root 3 times root 3 is 3. And the whole point is now you've rationalized the denominator, there's no square root down there. Alright, just a quick word on how the last two pictures are related. So if you take the short side over here and label this with some number, this is not how you'd normally start, right? But whatever number you end up choosing for the short side in both of these pictures, let's say you pick a 5, okay? Or if you had picked the correct number earlier, you might end up with a 5 over here. The hypotenuse side in both of these pictures end up being double the short side. Okay, so you'll have a 10 there and you'll have a 10 there. Again, don't memorize this as some sort of fact, but the whole point is you can find, the whole point was that you started with 10, this was the equilateral side of the triangle, and then this 5 was this computed thing, which was half of that, right? So this happens to be true due to an equilateral triangle. And then this third side, z, over here and over here, you set up the Pythagorean theorem in both cases. You have z squared plus 5 squared is equal to 10 squared. I mean, this is the Pythagorean theorem for both of these pictures. And when you work this through, you should get that z over here is going to be equal to 5 root 3, and same thing over here, 5, oops, not over there, but over here you'll have 5 root 3. So that's how the 30-degree right triangle and the 60-degree right triangle are related. The whole point is, you know, there's really a 60-degree angle there, there's really a 30-degree angle there, and you can always just take one picture and sort of flip. If you flipped along this line right there, you'd get this picture anyway. Okay, as long as I have these pictures up, I should mention this. Now, people tend to make this mistake usually when dealing with a 30-degree triangle, but sometimes this happens with talking about this 60-degree, and actually the next example we'll look at with the 45-degree. But I'd like to look at a different triangle, fundamentally different triangle, still a right triangle. Okay, so there's a very famous right triangle whose short side is 3, whose mid-length side is 4, and whose hypotenuse is 5. And the reason that this triangle is so famous is because these numbers work so cleanly in the Pythagorean theorem. And the point is, this triangle could never be this triangle. Here's the reason why. This angle right there, okay, that angle is actually approximately, it turns out it's approximately 36.87 degrees. So while these two pictures may look quite similar, don't let the pictures deceive you. Here there's this 36-ish, 37-degree angle. Here there's an angle that's then slightly smaller than 60 degrees. So there's no relationship between these two triangles. Okay, last thing, thanks for sticking with me so far. We'll look at the case when theta is equal to 45 degrees. This case actually turns out to be a lot more pleasant than the previous one. What you should do is start with a square. And again, you can pick the length of any side of the square to be whatever you want. Maybe we'll just pick 1, copy that 1 everywhere else. And then just draw in a diagonal. I think for the purposes of trying to keep the convention of the angle we want in the lower left, it'll make most sense to draw this diagonal as opposed to the other one. Now there's this 90-degree angle here, that's just from the square, and this 90-degree angle over here was cut into two equal-sized 45-degree angles, and actually there's a 45-degree angle up there. So let's just take the part of the picture we need, that's this right triangle on the bottom part. Copy this over here. You have 45 degrees, and now here's this mystery third side. This time it's the hypotenuse, which is the unknown side. You have 1 squared plus 1 squared is equal to z squared from the Pythagorean theorem, so 1 plus 1 is 2. And then square root both sides. Don't forget the plus or minus sign, so z is plus or minus root 2, but the only number that makes sense, we're talking about a length, so z must be positive. So now we can instead of having the z labeled right there, we can have a root 2 instead. Now we have all of the three pieces that we need